this is Mrs. Baston, and today we're going to talk about heat flow. So this first set of notes for this particular unit will be a little bit of background information and some definitions. So what we're going to look at today is what is heat, and then how can heat be transferred. So you have a little bit of background on that from having done that activity where you could visualize how the heat was transferred when you started with different temperatures of blocks and water. So heat is a form of energy that's the result of the motion of atoms and molecules. So heat is a way that energy can be transferred. Heat is notated with a Q. So that's the variable that we'll use when we're doing calculations for heat. Temperature is a measure of that average kinetic energy of atoms or molecules. So heat is something that can't be measured directly. We don't have a piece of equipment that we can put into something to measure heat, but we do have thermometers that we can use to measure temperature. And that temperature allows us to have a better idea of the kinetic energy, which then can help us understand how that heat is being transferred. So when we're looking at the molecules, again, one of the things you saw yesterday was how the energy can move. So there's no sound on this video, but we're going to watch here first. So if you look at this, you can see how the hot molecules are moving a lot faster than the cold molecules. But then as soon as they remove that barrier, all of the molecules mix together, and then they come to a point where they reach what we call thermal equilibrium, to where they are sort of the same temperature, or an average of the same temperature. So we know that heat is always transferred from hot to cold. So the hotter object always transfers heat to the colder object. The other thing you'll look at today in this assignment is you're going to read an article and watch another video separately that talks about why cold doesn't exist, and while really it's more about just the transfer of heat. Another thing we have to define when we're talking about heat is the system versus the surroundings. Now, this is a little bit confusing because there's not really a definite definition for either one of these. The system is the part of the universe being studied, but as the researcher, you're the one that decides what the system is. So if we are doing labs in chemistry, the system is usually whatever is contained in the beaker, whatever is containing the chemical reaction that we're studying. The surroundings then is everything else. So in this case, the example that's on this slide, the system would be the water molecules, the water and the ice that's contained inside the glass, and then the surroundings would be everything else. So the glass, the cup, the air, etc. The other thing that we'll talk about as we move through this and do a couple labs is an open system versus a closed system. So this is a good example of an open system because it doesn't have a lid on it. And that's really how we would make an open versus a closed system in the lab that we have access to. And then a closed system would be if we put a lid on top of that container and our reaction was contained inside of a container that was closed. We also need to talk about systems that are endothermic versus exothermic. So an endothermic system is one, and the colors are kind of reversed on these two pictures, but endothermic is something that absorbs energy. So you can see in this first picture, this would be endothermic, and they're showing it that color because the system itself is increasing in temperature, but it's absorbing energy from the surroundings. So it's taking in energy. So in that case, we would have what we would label as a positive Q. The delta H is another way that we can notate heat. So we can notate heat for now either with an H or a Q. And we'll talk about, for now we can use these interchangeably, and then later on when you come back to AP Chemistry, we'll talk about a little bit about the difference between those two. But for what we're doing in this chapter, we're going to interchange those two. So you can either use delta H or Q. So those values are positive. The signs in this case are going to tell us more about the direction of the energy flow than they are about the magnitude of the amount. So if you have a positive Q or a positive delta H, that means that that amount of energy is going into the system, or it's absorbing energy, or we would say it's endothermic. An exothermic system is one in which energy is leaving the system. So that's why this is showing this as blue, because the system is losing heat to the surroundings. So in that case, that's a system that releases energy. So energy is being released, so we would use a negative delta H or a negative Q to show that that energy is being given off. In simple terms, an endothermic reaction that tends to feel cold. If the temperature change is big enough, then it'll feel cold, whereas an exothermic reaction will feel hot because it's releasing heat. There's a couple different ways that heat can be transferred. So heat can be transferred by conduction. So conduction is when you have molecules that are in contact with one another. So if you touch, and this picture is a good example because it shows all three. Conduction would be if you touched a hot pan and you felt the heat and that heat was transferred from the handle of the hot pan to your hand, that would be conduction because there's direct contact. Convection is transfer by physical motion of masses of fluids. And this could be, convection can happen in liquids, it can happen in gases. Some of you may have a convection oven at home that circulates the air inside the oven. That's another way to transfer heat. So that's what that term convection oven means. So gases can transfer heat. Liquids can transfer heat. So in this example here in this picture, you can see the liquids transferring the heat in the water in the pan. And then the last one is radiation. Radiation is transferred by electromagnetic radiation. So in this case, you have the heat underneath or the fire underneath the pan, and that's transferring by electromagnetic radiation. So it doesn't have to be direct contact. So when you go outside and you feel the heat of the sun, that would be an example of heat transferred by radiation. Another thing as we start getting ready to do calculations in the next section is looking at some of the units. So the first unit, and the unit that we'll use the most, is the joule. So this is different than the joule that most of you are familiar with. The joule is Joule, and that is a unit of energy. So when we describe how the amount of energy, we're going to most of the time use joules, or we could use kilojoules depending on how much energy is released. So 1,000 joules is 1 kilojoule. So there'll be some calculations that we do where we will have to do some conversions with that. A calorie with a big C is a amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So technically this C here should be a lowercase because this is what we're looking at. So a little calorie is equal to 4.18 joules. A nutritional calorie is what we would call a kilocalorie or a kcal. That's equal to 1,000 little calories. So again, we'll do we might try to do some virtual labs with this where we can actually see how when you look at food or you burn different types of food, you can actually figure out how many calories are contained in that, and that's where they get that information on the nutritional label. So a little calorie, CAL, is equal to 4.18 joules. Nutritional calories that we're familiar with when we look on the back of a package of food, those are technically kilocalories. Heat capacity is another thing we'll talk about a lot. This is how much, or the temperature change that's experienced by an object when it absorbs a certain amount of heat. So how much heat is something able to take on before it starts to change temperature. And then specific heat is a constant that's notated with a lowercase c. And that constant is how much, or the heat capacity of 1 gram of a substance. So specific heat is how much heat is necessary to change 1 gram of a substance by 1 degree Celsius. So basically, how much heat can it take on before the temperature changes? And for specific heat, it's per 1 gram. So because we're talking about heat transfer, we're going to talk a lot about temperature. These are the temperature scales, and only one of these we'll use in this particular unit, and then we'll come back to another one when we study gases later on. So Fahrenheit is the one that we're most familiar with. So water freezes at 32 and it boils at 212. Those are the temperatures that we're most familiar with, and some of you had those conversations in that last chapter when we did the reaction rate challenge lab, when you were trying to figure out how hot the water had to be to boil. In Celsius, which is the temperature scale that we're going to use for this unit, Water freezes at 0 degrees and it boils at 100 degrees. Kelvin is used when we're talking about gases and some other higher level thermochemistry concepts. So in Kelvin, water freezes at 273 and boils at 373. And on the Kelvin temperature scale, absolute zero is 0 Kelvin. So 0K we call absolute zero. And this is technically the lowest, or theoretically, the lowest possible temperature. So if you could get something to that exactly that temperature, then all particle motion would stop. That's 0 Kelvin. And to get from Kelvin to Celsius, all you have to do is add 273 to degrees Celsius. And we'll do a little bit of temperature conversion, but for the most part, we will focus on using Celsius in this particular chapter. So here's a comparison of those three. So you can see the boiling point, 212 Fahrenheit, which is what we're used to, 100 degrees Celsius or 373 Kelvin. Freezing point, 32 degrees Fahrenheit, 0 degrees Celsius, 273 Kelvin. So you can see that the Kelvin temperature scale is a very different scale to what we're familiar with. Just to kind of give you an idea of what room temperature would be, in Fahrenheit, room temperature is around 70 degrees or so. Usually room temperature in Celsius is considered 25 degrees Celsius is usually given. Somewhere between 22 and 25 degrees Celsius would be considered room temperature. This scale here kind of gives you an idea of a comparison of those three. So what we're familiar with, Fahrenheit, if it's 0 degrees, it's really cold outside. If it's 100 degrees, it's really hot outside. In the Celsius temperature scale, if it's 0 degrees, it's fairly cold outside, but we're not going to be walking around if it's 100 degrees Celsius for our body temperature at least. And then Kelvin, 0 Kelvin, we could not tolerate. 100 Kelvin, we could not tolerate. So it's a very different temperature scale.